Okay, this is about charged particles, questions on charged particles, which typically involve looking at questions involving electric fields and magnetic fields. Here is a mass spectrometer used to work out the masses of various charged ions by accelerating them through an electric field, giving them a particular velocity, and then selecting the velocity using a magnetic field generated by an electromagnet. So all questions, or most questions in this topic, revolve around such apparatus. Right, now, number one, an electron beam is accelerated with a potential difference of 250 volts, and they enter a region of uniform magnetic field perpendicular to the beam of strength 0.02 Tesla. A. Calculate the speed and kinetic energy of the electrons when they leave the electron gun. So the gain in kinetic energy, first of all, will equal the work done on the electrons by the electric field, which consists of a 250 volt potential difference across a certain distance we're not given, but we don't need that, of course. We can use the equation E for the electric, so the electron's charge times V, and multiplying 1.6 to the power of negative 19 by 250 gives us the answer as 4 times 10 to the negative 17 joules. So that's the kinetic energy. And of course we can rearrange the half mv squared formula for kinetic energy and equate this number we just calculated to that and solve for V. We need to know the mass of the electron, which we do. It's given in the data table as 9.1 times 10 to the power of negative 31 kgs. So that we can use that. So just rearranging and solving for V is the only tricky bit, really. Once you've done that, you should get this answer. Just a tad over 9 million meters per second. So the question, same question continued, part B. If the anode and the cathode are separated by 1.6 centimeters, calculate the acceleration of an electron between these electrodes. A couple of ways of doing this. We could find the electric field strength and then find the force and then find the acceleration. But we could just use kinematics, so I'll use kinematics. V squared equals U squared plus 2AS. Solving for A, assuming U to be 0, because that's a fair assumption. And we just found V before, so I'm just making sure to change the displacement S into meters. Rearranging that, you should use this. We get a value 2.74 times 10 to the 15 meters per second squared. Part C, an electric field is now applied so that the electrostatic force opposes the magnetic force on the electrons and the beam goes straight. Calculate the size of the electric field. This means that the two forces, one due to magnetic field, one due to electric field, are exactly equal and opposite. So we can equate BeV for the magnetic force on the electrons to capital E, small e, the force due to the electric field. And of course rearranging the e's cancel out nicely, so we get V, the velocity, as the ratio of the two field strengths, electric over magnetic. Now we need to find electric field, so it's simply V times B, and substituting those numbers in gives us 1.87 times 10 to the 5 newtons per coulomb. Right, question 2. Calculate the magnetic field strength required to deflect electrons into a circle of radius 8 centimeters if the accelerating voltage in the electron gun is 400 volts. Now that 400 volts, of course, will give us a particular final velocity for the electrons emerging from the gun, and we can calculate that using the similar idea we just looked at before in the beginning of question 1, where the work done, let's do that again, work done equals the gain in kinetic energy, okay, which of course equals half mv squared, and that work done, of course, came from the electric field acting with 400 volts potential difference. So we just use VE. So we can rearrange and solve for V straight away using that idea. V, the velocity, that is, small v, would be equal to twice the voltage times the electric charge on one electron divided by its mass, all square rooted. Now, plugging the values in, you should get 1.1, we'll take a few figures here, 868 times 10 to the power 7 meters per second, just to avoid rounding error later. We're going to use that figure now to calculate the magnetic field strength, B, required to keep electrons moving at that speed, at that velocity, to move into a radius. Of course, we need a centripetal force, so we can say, well, BeV, our magnetic force, has to be the source of our centripetal force, mv squared over r. You can see that, of course, we can get rid of a square here and solve for B. We have everything else. In that case, so we have B equals mv over re, where m is the mass of the electrons, v is the velocity of the electrons, r is the radius, 0.08 meters that is required, and e, of course, the charge on a single electron. Now, plugging those numbers in gives us 8.43 times 10 to the power of -4 Tesla. So question 3, a student repeated Millikan's oil drop experiment and measured the charge on a number of different drops. The results obtained are shown in the table below. Using these results, obtain a value for E, the elementary charge. So this is a fairly standard question. You've probably come across it already. If not, maybe in the assignment or certainly in past papers. The idea is to add up all the charge and divide by the number of likely charges, values of E that each of those oil drops contain. So you can see this first one looks like a single elementary charge. This one looks like 2 elementary charges. So far we've had 3, 1, 2, 3, 4. This looks like 3. You can check it just by dividing by 3, and so on. So if you sum up all the number of likely charges involved, it comes to 16. By my count, but you check it yourself. When I did this before, just before, what did I get? A big long string. So you have to add up all these numbers and divide by 16 is basically what you're doing. But to work out the 16, I guess, is the tricky bit. So if you do that, you should get 1.61 to 3 significant figures as the size of the electric charge on one electron.